Our next speaker, continuing with the conference, Ivan Vergiliev, also known as Joe, because Ivan and Joe are the same names. He's a technical team lead at Heap Analytics, which, how many of you know the company? Heap Analytics? Right, that's plenty. It's pretty good. So Joe, I know him personally. We studied in the same school, and he's like one of the smartest people that I know. And he's actually the main guy who brought me to programming. It was because of him I started coding, and I became eventually a programmer. So I owe him a big deal. And he's going to talk about something really interesting when you have one machine that's running something and this machine is not enough and you have to scale out. And he will do it. I believe he'll do a great talk. So please, a big round of applause for Joe or Ivan. Take it away.
Okay, hey everyone. My name is Ivan, as Radu said, and I'll be talking about scaling out. Okay, so for starters, what does scaling mean? Scaling means that you take a system that is working for some volume of work, some amount of work, and you make it work for a different volume of work. So for example, this could mean it has more users, more data, more slower requests, or whatever. We usually talk about scaling up, like scaling to more amounts of data, more amounts of users. But there's also a useful concept of scaling down, which is like if you use something huge, it's not going to scale down to small amounts of users. We're not going to be talking too much about that tomorrow, but it's useful to know. So there are two main types of scaling. One is called vertical scaling. Vertical scaling means that when you start with a simple system. Where's the pointer? Okay, anyway. You start with a simple system, and when you need to scale it, so for example, you have 1,000 users and everything is working just fine, and then you do something and you suddenly have 2,000 users. So what you do then is just you take a machine that's 2 times larger, and you literally just replace your machine with a 2 times larger machine, and that handles your scaling concerns. And that's usually the simpler thing to do, but it has obvious limits, because everything is still running on one machine, and the only way you can scale is by getting bigger and bigger machines, and there's a limit to how big those machines can get. If you have to serve a large amount of the people in the world, like if you're Facebook or Google, there's no way you can get one machine to serve them all. So there's the other way, which is called horizontal scaling. Horizontal scaling means that you have those 1,000 users on the left, and then you get to 2,000 users, and what you do is instead of getting 2 times larger machine, you get 2 machines that are roughly the same size. And this is a bit harder to coordinate and to program, because now you have 2 machines that you need to take care of, but it has much better scalability characteristics. So if you're Google or Facebook and you need to handle another 1 billion of users, what you do is you open another data center. I think the most recent one by Facebook was opened in Singapore. So you just open a new data center, you buy a few thousand machines, and you just scale to them. So it's nearly limitless. So we're going to be speaking about that today. There's a lot to say about vertical scaling as well, but we're not going to be covering that today. So there are a couple of things I want to cover before I start with the actual talk, the actual content of the talk. First is a sentiment that I hear fairly often when I talk about scaling with someone. It's something along the lines of, sure, yeah, I read Hacker News too. Like, I know this exists, but you're never going to need it. Like, with the spirit that you don't need to care about scaling. And this hasn't been my experience, and it doesn't need to be your experience either. I'm going to tell you a bit about myself. So I've had to think about scale ever since I did my internships at Google and Facebook. And I remember that I had this one experience when I was wondering if I should handle some error case, which I expected to happen about roughly once every million requests. So I went to one of the senior engineers and I was like, look, there's this thing that's probably going to fail every once in a million or so requests. What should I do? Should I just like log it? Should I put an alert somewhere? Whatever. He's like, well, if it happens with a 1 in a million chance, we're Google, so it's going to happen like every few hours, like once every few minutes, so a bunch of times every hour. So you better take care of it, because if it breaks every hour, then things are gonna be bad. So scale is a thing that constantly need to think about if you work at a company like this. After that, I've worked at a number of different companies that also needed to scale out. I led the development of Limplums. How many of you know about Limplum? Because Heap is apparently not so popular. Okay, yeah, Limplum is more popular because they have presence in Bulgaria. But I led the development of the analytics infrastructure there, which is currently, they're still using, I think it's currently at about 200, 300 machines on about 2,000 CPUs. Currently at Heap, which is an analytics company based in San Francisco, we have about 1 petabyte of data stored on a 50-machine Postgres cluster. I think it's one of the larger Postgres clusters around. Although, on the other hand, I researched this a few days ago, and it turns out that Yahoo had a cluster about the same size 10 years ago. But they're Yahoo, so that's fine. So what I'm saying is these companies exist. Some of them even exist in Bulgaria. And because of their growth and because of how huge they are, they're actually hiring most of the time. So if you think about these things and they're interesting to you, you don't need to be satisfied by the fact that, oh, I can read about them on Hacker News, and you can try to find some place where you can apply your skills and learn new skills in production. Okay, the other thing we should cover before going further, computers nowadays are really, really, really fast. So if you use, for example, Amazon Web Services, you can get a machine that is called, Amazon has different machine types. And one of the machine types is called X1E. I think they just launched this a few weeks ago. But the one X1E machine, the largest of the machine types, has 128 CPUs and 3,904 gigabytes of RAM. No, this is 4 terabytes of RAM, not 4 terabytes of hard disk space. So if you have a website or something like this, and each request needs 10 milliseconds and 300 megabytes of RAM, which is plenty. Like you can do everything, but you can do a lot of stuff. You can serve 12,000 users, concurrent users, on the same machine. Not 12,000 total users, so not like 12,000 registered users. 12,000 users making a request right now. So like this whole and 11 more of it can be handled on this one machine. So basically, if you can, you should stick to a single machine. But if you can't, there are things to do. Okay, so let's start scaling. How we're going to structure this is we're going to start with a very simple web application backend. We're going to go through different stages in order to make it scale to more and more larger amounts of volume. And we're going to see a ton of architecture diagrams. If anything is unclear at any point, feel free to interrupt and ask. Okay, so we start with something simple. We start with a monolith. It gets a request, it returns a response, and that's it. Everything is in the same place. And it just works, and it's simple. It's a nice place to start. But then at some point, you realize that, oh, okay, now my monolith, because it's very simple to develop, is actually ready for some production exposure. So I'm ready to show it to users and get more users. So you launch a huge marketing campaign. And your marketing campaign results in, well, a ton of hits to your marketing page. It doesn't result in a lot of signups. It's not very great for, like, the conversion rate is not awesome, which is not great for business, but it's nice for scaling your architecture because it's actually a simple problem. So what we see here is, so the examples are made up, but they are generally realistic. So what we see here is the number of requests to static files, say something like static/index.js. And these are supposedly things that are run on your marketing page. And then the number of requests to your, for example, /login. So the number of people who log into your site is much lower than the number of users who need to access static files. By the way, does anyone know why I've put this sinusoid here? Like, why is there a sign? Why is it like this? Has anyone seen this pattern? Anyone? Yeah, someone's raising hands there. Go ahead. Yeah, exactly. So this is usually a very standard day and night pattern. Usually during the day, there are more users using your website. During the night, not so many, but still some. And the interesting thing is that even if you're a worldwide company and you have customers all over the world, this is still a pattern that you see. And usually it's the high part is the US day and part of the start of the European day. And the low part is the European day. Because the people in the US are still more active, and at least like they're more active for most of the platforms that are up there that appear worldwide. Of course, if you have something that's based in Europe, it's going to be the opposite. But and this is very useful if you have an American company with people who work in it in non-US time zones because you can do deploys during the low times. So it's very nice. Anyway, so we have this thing. We have a lot of requests to static files, and they're starting to get kind of slow. So what can we do about this? Well, the cool thing to notice is that your marketing page doesn't actually run any of your application logic. So it's a very limited problem to solve. You don't need to scale your whole application in your whole database. You just need to scale serving your static files. And serving static files is kind of a simple problem. It has 3 main steps, very simplified, of course. But the first one is read the file from disk. The second one is return the file to the client. And the third one, which is not really a step, is do it all really, really fast. And basically anything can do the first 2 points. Like you can start a Python one-liner that does the first 2 points, like it starts a HTTP server and it serves files from a given file directory. But the third point is a bit more complicated. But still, there are things that exist that can solve this problem really well. So what we can do is we can split the two. So we can put the backend separately and the static files separately. For the static files, we can use something like Nginx. Nginx is a web server. Web server is probably not an accurate term, but it's a server that is written in C, and it's like super efficient, and it can scale to probably much higher than, like certainly much higher than, for example, your Node.js or Python or even Java app can scale to serving static files. So what you do is have the Nginx server static files, have the dynamic stuff go to the backend, and you put a reverse proxy in the front. So now, what is a reverse proxy? Well, the reverse proxy is the thing that your clients are gonna go to now. So when there's a request, it goes to the reverse proxy. And the reverse proxy determines, based on the request path, where the request should go. If it's dynamic and it requires application logic, it goes to the backend. If it's static, it goes to Nginx. So your clients, like your users, the users of your website, don't really know that there are 2 separate things in the front, in the back, because at the front there is a reverse proxy that handles all this for them. Okay, so eventually your marketing efforts start to pay off, and there's some growth to the login page as well, and some other application pages. So as a result, your database starts taking some hits as well, and it's having problem scaling. So what we can do is take it to and move it to a separate machine. The green things here are usually separate machines. So the database machine. So basically, we take the database and we move it to a separate machine. It's a very simple thing because the database and your application code are actually very nicely decoupled. So you can just move the database, and this allows you to do nice things like scale it separately. For example, your database might need a lot of, like a very fast hard drive or an SSD or whatever, and your application code might need a lot of CPU. And you can scale, you can get a very fast, very CPU-heavy machine with a lot of CPUs for the application code and a machine with a lot of RAM and a very fast disk for the database. You can scale them separately, and it's all nice and good. Okay, so now let's go to something a bit more complicated. So now we have this pattern here. The blue line is the database update capacity. This is roughly how many data updates your database can run per second. For example, let's say this is 250. So your database can run roughly 250 updates per second. This is like, it's obviously not going to be a straight line, but let's imagine that it is. And this one is the usage pattern. So how many database updates we actually try to do. And so notice that most of the time, it's lower than the 250 that the database can do. But every now and then it spikes. And it spikes to, for example, 300. And if we try to write these 300 requests directly to the database, we're going to drop some data because the database cannot handle them. So what can we do about this? Well, here's a nice thing. Notice the areas of this graph. So the area under the curve, some math time. If you integrate it, that's the total number of requests that you need to write to the database. So basically, what I'm saying is that this part here can fit very nicely in this part here. So if you take the updates that are above the update capacity of the database during your high load times of the day, and you apply them during low update times of the day, the database can handle all of this. So the database is capable of handling all the requests for a given day, It's just not capable of doing it at the same time that they arrive. So what can we do about this? Well, we can decouple the time that we receive the message from the time that we write the message. How do we do that? Well, we can use a message queue. What is a message queue? A message queue is something where we put messages, obviously. And in our message queue, we can put things like write event with ID 5 and type click to database table events. Then write event of type 10 with ID 10 and type payment to the database table events. Then update user with ID 33 and set the country to equal Bulgaria to database users, and so on and so on. And we can put things in this database. So when a write comes in and you need to update something in the database, instead of going directly to the database and updating it, you put it into the queue. And then there's a consumer which reads things from the queue, and it writes them to the database. So what does this mean? It means that we have decoupled the time that we receive the events. So when we receive the events, we just write them to the database, to the queue, sorry. And then the consumer reads them at a different time. And the consumer can read them at the time that is appropriate to the database. So if there's a very high load at a given moment, the consumer can slow down and only consume as many messages as the database can write. And when there's free capacity, the consumer can actually catch up and consume more messages and make the queue all written to the database properly. So the nice thing about this is that the queue has a very simple task. It takes a message, which is usually serialized as a string. It's literally the string, write the event to the table events. It's like, take these 100 bytes of data and put them on the disk and make sure that it's there permanently. It doesn't need to update any indexes. It doesn't need to handle concurrency. Well, it needs to handle concurrency. But it's just important at the database level. And it doesn't need to handle all kinds of other things like triggers or whatever that your database has, depending on how complicated it is. So because it's a very simple task, you can take some software that implements it very efficiently. So what does our whole infrastructure look like now? So we have the reverse proxy here. It's basically the same to this level. But now the backend, instead of writing and reading directly to the database, it reads from the database, but it sends some of the writes to a message queue. The message queue I've put a RabbitMQ as an example. RabbitMQ is one of the most well-known message queues around, but you can put other things as well. And then there's a consumer, which is some application that reads messages from the RabbitMQ, and it puts them into the database. Now notice one detail. I've put immediate writes here. I don't know if you guys can actually read this, probably not. But yeah, so basically I've split the writes into delayed writes and immediate writes. Why did I do that? Well, the thing about the message queue is that it causes a delay to when your updates show into the database. So if you can do something like, say you're browsing Amazon and you add a thing to cart. You're looking at the book and you say, okay, add to cart, I want to buy this. And if we just dump everything into the message queue, this would send a message to the message queue saying, okay, insert the message add to cart, or like update the cart with something like this, with the item that he chose. And then if there's a delay, this message is going to be applied at a later time. So if I go immediately to my cart and they show it, it's not going to show the thing that they wanted to show. So we probably want to keep some of the immediate writes here. And so the things that actually have user visible effects, we want to keep writing them immediately. But the things that are that can be delayed, we can write them to the message queue. So things are getting a bit more complicated, but it's still feasible. Yeah, this is what I explained. The technical term for consistency models is usually read your writes, because I wrote something to the database, which is update my cart, and then I couldn't read it if I just put things into the queue. Okay, so far this is pretty nice. We separated the different functionalities on the separate functionalities now live on separate machines. And this is so cool. It's a pretty nice architecture because it allows you to do certain things, like analyzing the usage patterns of the different services is nicer. For example, if you see that there's a lot of CPU load on the backend machine, this usually just means that there's a lot of load happening in your application code. It's not caused by serving static files because the static files are not there. It's not caused by the database slowing down because of like complicated transactions, because the database isn't there either. So it's like much easier to analyze. But the fun part comes next. The fun part is when individual functionalities don't fit on individual machines anymore. So same pattern. You get a next funding route. You have more money now. So you launch another marketing campaign, and your marketing site is almost literally on fire. And you need to scale it. Again, this is probably not what you were hoping that your marketing money is going to buy you, but this is how it starts. So the problem is with the Nginx here. It's a single instance, and it needs to do a ton of reading from disk and a ton of sending to the network and stuff like this. So what can you do about this? Well, you can put a load balancer in front of it and start multiple instances. Is that visible? Okay, it's fine, cool. Yeah, so you put multiple Nginx servers, and you put a load balancer in front of them. So now, the reverse proxy, when it needs a static file, it doesn't go directly to one of the Nginx servers. It goes to the load balancer. The load balancer says, oh, okay, I see that the third machine has a very low load now, so I can send it more requests, and it's going to respond quickly. And the nice thing is that all the servers are serving the same content. Basically, there's still no application logic happening on them. There's all the static files that you're serving are the same. There's nothing that you don't need to care about the separate service and do things separately for each of them. But there's one gotcha. The gotcha is that we need to be careful with deploys. So when we're deploying new versions of the static assets, if we're not careful, we can get to a situation that's like this. We're deploying a new version, and so this Nginx server ended up with static access of version A. And this Nginx server ended up with static assets version B. So now a user makes a request for /static/index.js, and it gets to the first version. And it gets, for example, the user gets the old version of the index.js. And then the main.css request goes to the new version. So we deployed a new version. It's completely different. All the selectors are different. And now the index.js doesn't work with the main.css that we supply to the same user. So there can be a broken experience with the users. Does that make sense? Okay. So there's a way to solve this. It's not a super hard problem, but it's something that we need to take care of. Okay. So we solved this. We have this nice cluster of Nginx instances. It's all cool. So next, we finally hit a point where our application code is causing load issues. So the marketing site is on fire, but we solved that. And then there's like the conversion is finally going up. So we have actually load issues in our website, on our application code. So the problem now in the architecture is here. The problem in the component is this one. So we take our backend, and what should we do about it? So the nice thing is that, again, as mentioned with the Nginx requests, all the servers the server is doing the same thing. So what we can do is just replicate it. So we can start multiple application servers. We start like 4 or 10 or 100 application servers, and they're all running the same code. And we put a load balancer in front of them, and the load balancer says, okay, I see that this one is low on CPU usage and memory usage, so I can send another request to it. And because the requests are all the same, the application servers can handle them just fine, and you can rotate between them however you want. Now, again, this is all nice, but we need to be careful about a couple of things. First is, again, deploys. If we're deploying the servers one by one, we can get to a state where a user does a post message, for example, to one of the servers, and it executes application code version A, and then it executes get messages on application code version B, and for some reason that shows inconsistent results. And that's not a nice user experience, but we can also solve it with similar approaches to the Nginx deploy situation. And there's another thing that we need to be careful about here. It's session state that's stored in memory. So when basically HTTP is a request response protocol. So there's supposedly it's sessionless. Nothing is saved between the requests. But in practice, most of the websites treat your usage of the website as an actual session. So if you start 10 requests, there's going to be some stuff that is remembered about you throughout all the 10 requests. And for example, when you start the first one, there's going to be some stuff put into the session. And the second request is going to try to use this stuff. And if it doesn't find it, it's going to treat you as having a new session. So if we just put the session state into memory on the different servers, this can result in the load balancer sending the first request for a given user, say X, to this server, and the session state is here. So the session started here, so the session state is in memory on this server. And then when the user starts a second request here, there's no session state. So we don't know what's happening, and we just treat them as a new user, which is annoying. The usual way to solve this is not to store session state in memory. We store it in a separate place like a Redis or some kind of in-memory-like database, but not on the machines themselves. Okay, so now we solve this problem as well. And now we get to a point where we realize, okay, we have a ton of users, but they're not actually doing exactly what we expected them to do. We ended up with a lot of users that are like passive consumers. So the database reads are much, much higher than the database writes that you have. Now, this might seem like somewhat made up, but it's actually a very realistic example. It's a very safe assumption. Facebook published a paper about a distributed system called Tau that they use for storing their social graph. They built it. They don't just use it. But they reported some of the usage metrics. And the usage metrics that they reported say that only 0.2% of the total requests to the system are actually update requests. So they optimized very, very heavily with a lot of caches and a lot of things that are optimized for handling read requests, putting those components into the database, because the writes are actually a much lower part of what they need to do. So, okay, now we have the same problem as Facebook. And if you think about it, if you think about how you use your social networks and stuff, you probably realize that that's what you do most of the time. It's like scrolling through things and viewing posts, viewing photos, etc. And it's not actively producing content. I think, again, kind of disappointing for retention, not great for your business, but it helps with the architecture. What we can do here is make the database part a bit more complicated. So now, instead of sending all the reads and all the writes to the database, as we did before, so we had the reads and the writes go to the database, except for some of the writes. Now we can separate them and have the writes go to the primary database, and then have a cluster of read replicas that are replicating actively the primary database. What does that mean? Well, it means that they take all the things that happen in the primary database and they apply them locally to their own databases. So they have the same content, so you can send reads to them. So if your read is like 10 times larger, your read volume is 10 times larger than your write volume, you can just launch 10 read replicas and read from them instead of the primary database. It's also pretty nice. Now the thing that we need to take care about here is stale reads. So stale reads, as I said, the read replicas take the messages from your main database and they apply them themselves. But that means that there's a similar effect to the queue here, to the RabbitMQ layer. So the database replicas might be behind. So you applied some messages to the primary database and they have not yet been applied to the read replica that you're using. So we need to think about this as well. Okay, so our architecture is getting a bit more complicated. We have all these components, everything is scaled up nicely. So like for fun, let's look at something a bit more extreme. We got the main thing scaled. We got the database, we got the application code, we got the static asset serving. So what could be next? Like what could be our next problem? And just like hypothetically, let's look at the reverse proxy. Now, the handling all the requests is very nicely scaled up, but every single request still passes through the reverse proxy. So it kind of makes sense that the reverse proxy might actually become a bottleneck at some point. So what can we do about it? Well, we can start multiple reverse proxies. It's as easy as this. It's not actually as easy as this, because before, the reverse proxy was the thing that the clients accessed from our website. So now what do the clients access? There's no single IP, there's no single machine that they can go to. We can put one other reverse proxy at the front, but that's not really gonna solve our problem because it's still gonna have all the data passing through it, right? So what we do here, how does the client know which reverse proxy to contact? What we usually do here is use DNS round robin, which means that we have the DNS have all the IPs for our multiple load balancers. And when the client makes a request to the DNS, it sends, I think it sends all the IPs, and then the client decides which IP to query. So we get a nice load balancing without having any single machine get all the requests go through it. And I'm gonna tell you a bit briefly about an actual production incident that we had with something similar. So AWS, Amazon Web Services, provides something called the Elastic Load Balancer. So the Elastic Load Balancer basically handles the parts that I mentioned about having multiple reverse proxies. And it's actually even nicer. Well, it also handles the parts about updating the DNS. So you don't need to take care of this. You get it for free, generally. And the even nicer thing is that it's elastic, which means that it scales out as you need. So that means that if during the night you need only 2 load balancers, it's gonna start 2 load balancers. But during the day, if you have like 3 times more load, it's gonna start 3 more load balancers and have a total of 5. So it can scale up to your traffic. It can scale up to traffic spikes, which sounds awesome, except in some exceptions. So we had a case a couple of years ago. Remember when in 2016 the people of the United States of America chose Trump for president? So then at about the same time, at exactly the same time, we had the other candidate. We had Hillary as a client on our website. And the fun thing was that their website would usually get a fairly low amount of volume, like a normal volume, like people are checking out your campaign website. It's not that fun. It's not very engaging, but you check it out because you want to decide who to vote for. But then, suddenly, a debate comes. And Hillary comes and says, oh, here's my website. Go and check it out. And suddenly, now you have 10 times more requests. And so the problem that we hit with this was that Amazon couldn't scale out the elastic load balancer fast enough. So it would scale out eventually, and it would get to like the volume that we needed in order to handle the 10x more requests from Hillary. But the problem is that we would lose a few minutes of requests because the load balancing is not actually fast enough, the elastic part. So what we did was we handled it ourselves. A few minutes before the debate started, we launched a ton of fake requests to our own elastic load balancer to basically hint AWS, here, there's a storm coming, scale out as fast as you could. And that's how it solved our problem. Okay, so the talk was called Scaling Out from First Principles. So what are the principles? These are like one-liners that I made up that are obviously not gonna cover all your scaling concerns, but they should hopefully give you like at least a basic framework of how to think about this. Split it into when, what, and how. So when should you scale? I think the answer to when should you scale is usually shortly before the load because too much for the current system. Why not scale earlier? Well, okay, which one would you rather maintain, the one on the left or the one on the right? I usually prefer to talk about the one on the left because I don't know, I can't even see what is on the right. And also notice we need to think about this as we went to the presentation. In the beginning, there was like barely anything to be careful about. And then as we went on, there were more and more things that we need to be careful about when any single component to the system. And also, basically any single component that you add, especially the distributed ones, requires knowledge and maintenance, and even if they are production tested. For example, we've been using Kafka, which is a very, very well production tested queuing system used at LinkedIn at very ridiculously high volumes. And we've been using it for like 3 years. And still last year, we had to spend about a month trying to rebalance the cluster because of some lackings in the software. So anything that you add earlier than necessary is gonna be a cost that you pay earlier than you have to. Why scale before the load is too much? Well, just because from practical reasons, your new system that you develop, for example, if you decide to replace your database with a database with 3 replicas. It's going to require some application changes, some changes to your deployment, etc. And this is, realistically speaking, it's not going to be perfect. So it's very nice to know that when things go wrong when you deploy the first time, there's an existing system that can still handle all your load. So you can just go back to it. And if you wait until the load is too much for the old system to replace it with a new system, then there's nothing to go back to. If anything doesn't work, you're screwed. Okay, what should you scale? So the answer here is find the bottleneck in the existing system and scale that. Notice that each time, like for example, the first time we tried to see that the bottleneck is actually serving the starting files. So we didn't just go ahead and like scale out the application code. We separated the static files and we solved the actual bottleneck of the system. But the question now is, so the thing is that if you don't scale the bottleneck but you scale something else, it's not going to solve your problem. That's true in team systems as well as production systems. Like if your team is being slow, you need to figure out why it's being slow and solve the bottleneck instead of solving something random throughout the system. But now the question is, how do you find the bottleneck? And that's a bit tricky, especially in a large, very interconnected system, because, for example, you can have database load going high, delaying your queries. Your queries could start blocking and delaying your application servers, and this could actually serve as your application request being too slow and timing out. So your metrics and error messages would say, okay, this is the application error, an application error, but it's actually a database problem. So how do you find it? Well, a few things you can do. You should instrument the system very aggressively and look at the metrics. Looking at the metrics is something that I tried to show here. We would see some metrics, we would see some patterns in them, and we can use those patterns to actually find the bottleneck and realize what's slow and why it's slow. Next, you can profile the components. So you look at your application server and you start a profiler and see, okay, I have like 90% CPU usage. Where is all this CPU usage going? And for example, you might find that out of your 20 HTTP endpoints, one of them is actually consuming 85% of the CPU time. So you can do something to actually improve this part of the system. And the next part is you can load test the system. You can load test it with larger amounts of work to basically synthetically simulate the next marketing launch or the next big thing that causes your system to become overloaded, and see how the system behaves under that load test. And a nice trick that I like to use sometimes is load testing with dummy replacements. So the idea here is you load test the whole system, but you replace a single component with a dummy backend. For example, you can replace the dummy database with a database that takes on all your requests, but it doesn't actually write them to disk and it doesn't update the indexes. And if the limit to which you can scale your system now is still the same as before, then that means that the database is most likely not your problem. Because when you made it fast, it didn't change anything in the system. But if it actually made you take in like 10x more requests, then you probably need to optimize your database, and the backend and the Nginx layers don't really matter at this point. Okay, how should you scale? Find the simplest solution that will work for a reasonable amount of time. Why the simplest solution? Well, we already argued about hard solutions being hard to maintain when reasoned about. What does reasonable amount of time mean? Well, you should try to predict how your load is going to grow in the future. And if the system that you intend to load, well, yeah, you should do that based on metrics growth, based on intended like talk to sales or marketing departments, see if there are any upcoming marketing launches or huge clients that are coming on. And look at the metrics and how the system is going organically and so on, and try to predict the future and how it's going to grow. And if the new system that you want to replace a component with is very simple, but it's only going to solve your problem for a month and it takes 2 months to build, it's likely not worth it. You probably need to pick up something a bit more complex. And like overall, it's nice to think about evolving your architecture. So if we had started and stick to one of these architectures that we showed in the middle of the slides from the beginning, they all would have had their own drawbacks. So if we started with a very simple architecture, at some point we're just not going to be able to scale. And that's a problem that's happened. For example, I think MySpace is famous with collapsing under their own load. They couldn't scale the system fast enough, and they couldn't take on their own users and develop new features fast enough that scale with the system. If we started with the with the complicated endpoint architecture, first, we're going to take a long time to build it. And like time to market is an important thing. And second, for the whole time that we have it and don't need it, we're going to be paying the costs that all these distributed components and all these interactions require. So you should think about, at this point, how is my architecture looking and how should I evolve it? What can I do to make it better for the next few months, for the next few years? So I don't have to do like any hacks and stuff. I don't think we have any time for questions. So yeah, thanks.
Check. Like we have time for one question. Oh, I saw it over there. Can you stand up? Ready?
Me here? Normally? Yeah, thanks. For me, it's pretty much interesting. Thank you for, first of all, for your presentation. And like, I would like to know, for example, in your particular case, how many requests, for example, per second do you have? And main statements was about like, you cannot just scale. First of all, you need to profile things as application. After that, you need to perform some like load balancing things and then scale if needed. So would you like, could you please just to clarify what kind of frameworks you're using and like why exactly those frameworks? Thanks.
Okay. Yeah, so as I mentioned in the beginning, we store our database in a Postgres cluster. So we use something called SiteSDB. We have about 50 or something like this, very huge machines that store all our data. So we use SiteSDB to distribute our queries among the cluster. So basically the database part is handled by SiteSDB. The queue that we use for queuing at Heap is Kafka. We have a few Kafka machines, like I mentioned. The queuing problem is like much simpler than the database problem, so we have much less Kafka resources thrown at the problem. And then at the front, we actually have a Node.js server, which is not like the greatest thing for performance, but that's how we started. And we found that for the moment, scaling it out is actually more efficient than spending the time to rewrite all of it and having the risk to do that. And parts of the system, like the part that consumes messages from Kafka, sends them to the database and so on, is written in Scala. Some other parts are written in Scala as well. I don't know if that answers your question.
Very quick question, because you didn't talk about scaling the actual interesting part, which is the write database that handles the writes.
Yep.
Because all the others are basically stateless. You can just put more of them and put some kind of load balancing. How do you scale the writes and the actual synchronized writes?
Yeah. So that's the hard question. You usually, I think the most popular way to scale this is by using sharding. So sharding means that you partition your data horizontally. So you say all the user IDs that are between 1 and 1 million go to one machine. All the user IDs that are between 1 million and 2 million go to a different machine. And then you have some layer that knows where each record in your database is and directs for example, the writes and the reads to the right machines. And there are a lot of things that do this for you. You can use the thing that we use called the one called SiteSDB actually does this for us, parts of it for us. We do the sharding ourselves, and then we use SiteSDB to compile queries that are informed by the sharding information. So we tell SiteSDB, okay, if someone asks for users in this range, you should go to this machine. If they ask for users in this range, you should go to that machine. So SiteSDB takes our Postgres query, and it compiles it into separate queries for each of the workers. And so each of the queries on each of the workers is actually local, but there's a central component that compiles them throughout the cluster. You can use something like Cassandra. There are a lot of things that do the sharding for you, but that's the most popular strategy. You separate the data into the different databases and you handle it somehow.
All right. Well, thank you. Big round of applause.